Hello everyone. In this video I'm going to explain you the solution for the first problem of the midterm exam that we just had. So we need to draw the root locus sketch for the system provided here. GP is given as s plus 3 over the denominator, and GC of s is equal to the k. So we need to first form L of s, which is GC times GP. And for that we have k times s plus 3 over 5 times s plus 1 times s plus 2 times s plus 4 squared. And we can rewrite this as rho times s plus 3 over s plus 1 times s plus 2 times s plus 4 squared. So you can see that rho is equal to k over 5. So rho is k over 5. For n we have s plus 3, and for d of s for the denominator we have s plus 1 times s plus 2 times s plus 4 squared. This means that we have n equal to 1, 2, 3, 4. So we have 4 poles. M is equal to 1. We have 1, 0. Therefore, R, which is equal to n minus m, will be equal to 3. And this means that we have 3 asymptotes. There will be 3 asymptotes. For the asymptotes, we would need to find the point of abscissa and the angle of the asymptotes with their real axis. For xa, we know that it will be in the form of sum of zi's minus sum of pi's over n minus m. So we will have 3 at the denominator. For sum of zi's, we have 1, 0, which is 3. Minus for the poles, we have 1 plus 2 plus 4 plus 4. We have 2 poles at minus 4. And this will give us minus 8. So minus 8 over 3 will be the point of abscissa, xa. For the angle of the asymptotes with the real axis, we have r times ca equal to 2h plus 1 times pi, and 2h pi for the positive locus and negative locus, where h will be equal to 0, 1, and 2. And therefore, Ca will be equal to, if I replace h with the values and divide the both sides by r, which is equal to 3, we will have pi over 3, pi, and 5 pi over 3 for the positive locus, and we will have 0, 2 pi over 3, and 4 pi over 3. So 2 times 2, which will give us 4 pi over 3 for the negative locus. So we have the asymptotes in this way. We can start to prepare the drawing for the positive locus and negative locus. So I'll start by drawing the empty indeed S-planes for imaginary and real axis. And the first starting point would be to specify the open loop poles and zeros of the system. So we have a 0 at minus 3, a pole at minus 1, 1 at minus 2, and 2 at minus 4. So we'll have 1 pole at minus 1, minus 2, a 0 at minus 3, and 2 poles at minus 4. Minus 1, minus 2, minus 3, and minus 4. We can now draw the asymptotes for this system. let me use the blue color. We have the point of abscissa, which is minus 8.3 or minus 2.66. It will be somewhere here. For the positive locus, the angles are pi over 3, pi, and 5 pi over 3. So this will be somehow the asymptotes for the positive locus, and for negative locus we'll have 0, 2 pi over 3, and 4 pi over 3. So 0, 2 pi over 3, and 4 pi over 3. These are the asymptotes. The parts of the real axis which belong to the root locus for the positive locus and negative locus will be like the ones that I specify. So this part will belong to the root locus for the positive locus, and also this part belongs to the root locus. You just count the number of the poles and zeros to the right side. If that's an odd number, then it belongs to the positive locus. So for this segment, for example, we have 1 pole. For this segment we have 2 poles, so it doesn't belong, and for this segment we have 3, and then we have 5. And similarly for the negative locus, the parts of the real axis which belong to the root locus will be that segment, this segment, and that's it. So those two segments will belong to the root locus. Now we know that the branches will start from the open loop poles of the system, and they will go either towards the zeros or towards the infinity. We have two open loop poles over here, so one branch will start from there, another branch will start from here. They will meet at some point, which we can determine later, and then they will depart the real axis, and one will go towards infinity using that asymptote, and the one using this asymptote. The poles that are located at minus 4 will be moving on the real axis. One will go towards the 0 at minus 3, and the other one will go towards minus infinity. For the negative locus, the pole that we have at minus 1 will move towards infinity, plus infinity, using this branch, as the value of k increases with a negative sign. And then we have one pole which will approach the 0 here on the real axis. We have two poles at minus 4. They need to depart the real axis right over there, and I guess they will move towards infinity using the asymptotes in this way, because they can't lie on the real axis around the point minus 4. Alright, so for this system you can see that for the negative locus we will have a breakaway point at the point minus 4, that's for sure. We don't have any break-in point. For the positive locus we will have a breakaway point between minus 1 and minus 2. So it might be minus 1.5 or somewhere around there. If you want to find out the exact value for the break-in or breakaway points, we would need to solve m prime d minus n d prime equal to 0. But if you want to do that, you would need to find a solution to a polynomial of the fourth order, because for n we have s plus 3, n prime will be equal to 1, so that will be easy. But you would need to find out d prime first. It will be a polynomial of third order. It will be a third order polynomial. Then if you multiply it by n over here, you will get a fourth order polynomial. So basically you can form it and then find out the roots. One of the roots will be equal to minus 4, as I have shown you here. The other root will be in this area, and the other two might be they might be indeed complex conjugate. So we will use this. But for the purpose of this example, we don't need to find the exact values. You only need to know that they will be located at some place like that. Alright, so we we kind of have drawn the approximate root locus plot for these two systems. If you want to be specific, you would need to find out the point in which the branches cross the imaginary axis. You can apply the Rausowitz criterion, or you can use the other approach by indeed setting the imaginary part and the real part of the characteristics equation, and then setting them equal to 0. And out of that you can find the value for k, and you can find the exact value for where the branches cross the imaginary axis. The next point here is that for which values of k the system will be, for which value of k, one of the closed poles of the system will be located at s equal to -6. S equal to -6 belongs to our positive locus. So let's say it is this point. We know that rho will be positive. In order to find out the exact value of rho, we need to apply the amplitude condition. Amplitude of n over d will be equal to amplitude of -1 over rho. Amplitude of n will be obtained by replacing s equal to -6, or finding the distance of the 0 from that point, which is equal to 3, over amplitude of d will be equal to, we have two poles at -4, this is equal to 2, so 2 times 2 times the distance from 2 to there is 4, times the distance from 1 to there is equal to 5, and this is equal to amplitude of -1 over rho, and therefore we can find out the exact value for rho. Rho will be equal to, so we have 10 times 8, 80 over 3, and we know that rho is a positive value. On the other hand, rho is equal to k over 5, k over 5, therefore we can find the exact value for k. This is equal to k over 5, and as a result k will be equal to 5 times 80, 5 times 80 over 3, or 400 over 3. K will be almost equal to 133. For this value of k, one pole will be located at -6. The other poles will be located, one will be located somewhere here between -4 and -3, and the other two will be most likely be somewhere over here. If you want to find the exact values, you would need to replace k with the given value, and then solve n minus 1 plus rho n over d equal to 0. If you replace rho with that value, you will have d plus rho n equal to 0. You have the value for rho. You know that one of the roots will be located at -6, and then you solve it, you find the other 3 poles. But that's beyond the question that we have here. Okay, so then we need to determine the steady state error for the unit step response. For the closed loop system with the k value found from the previous step, we have k given. K is equal to 133, or k over 5 is also known, 80 over 3. So we have A log s, which is in the form of k over 5 times s plus 1 over the denominator is known with a given value of k. Therefore, we can find out kp for this. It's a type 0 system. Kp will be equal to 80 over 3 times 1 over, so for the denominator we have, no, for the numerator we have 3, so s plus 3. If I replace s with 0, we will have 3 over 1 times 2 times 4 squared. So kp will be equal to 3, and 3 will be neglected. they will cancel each other. So we'll have 80 over 2 times 16. If we divide this by 2, we will get 40. Divided by 4, we will get 10 over 4, which will be equal to 2.5. So Kp will be equal to 2.5. The steady state error for the unit step input will be equal to 1 over 1 plus Kp. So 1 over 1 plus 2.5, or 1 over 3.5. And this will give us the steady state error. The last point is that for which values of K the closed loop system will be stable. Okay, so to find out the solution for that, we can use the Ross-Horowitz criterion, or we can try to find out the value for the value of K where we change from a stable system to unstable system. And we need to determine it for these 2 points. Doing it for the negative locus is easier. Over here we can apply the amplitude condition, n over d equal to minus 1 over rho. So for n we will have 3, for the d we will have 4 times 4 times 2 times 1, and it's equal to minus 1 over rho. So rho will be equal to minus 32 over 3. And this is equal to K over 5. So K will be equal to minus 32 times 5 over 3. We know that if K becomes smaller than this value, minus 32 times 5 over 3, then the system will be unstable. If K is between this value, minus 32 times 5 over 3, and 0, the system will be stable. Now we need to find out the value for the K at this point. To find out the value of the K, or rho over here, we can form the d plus rho n, d plus rho times n equal to 0, and eventually we will end up with this fourth order polynomial over here. Then we know that at that intersection of the root locus branches with the j omega, or with the imaginary axis, s is equal to j omega. So we can form s squared, which will be equal to minus omega squared, s to the power of 3, which will be equal to minus j omega to the power of 3, and s to the power of 4, which will be equal to omega to the power of 4. Then if we replace all this into the equation, into the fourth order polynomial that we have over there, we can rewrite that equation in this form. So we will have omega to the power of 4 minus 11 j omega to the power of 3 minus 42 omega squared plus 64 plus rho times j omega plus 32 plus 3 times rho equal to 0. Now we need to place the real and imaginary parts of that equation separately, and then each one of them will be equal to 0, which will give us the values for the omega and also for the rho. So for the imaginary part, we will have minus 11 omega to the power of 3 from here, and also 64 plus rho times omega. So plus 64 plus rho times omega. For the real part, we will have omega to the power of 4 minus 42 omega squared plus 32 plus 3 rho for the real part in it. Yeah? If you look at the imaginary part, one root will be equal to omega will be equal to 0 as a as one root, and we can obtain the corresponding value of rho looking at the real part. If you replace omega with 0, we'll have rho equal to minus 32/3. And this is actually what we have found already over here by applying the amplitude condition. So here we had the value for rho as minus 32/3, and the value of omega is obviously equal to 0. So that's something that we already have, and we are not interested now in that value. But if we consider the rest of the equations that we have here, we have omega to the power of 4 minus 42 omega squared plus 32 plus 3 rho equal to 0. And from the imaginary part, we have minus 11 omega squared plus 64 plus rho equal to 0. We just need to solve these two equations. From here, we can obtain rho equal to 11 omega squared minus 64. And then replace this in the first equation, and out of that find the value for omega squared. If you do so, you will get omega squared equal to 17.92. And replacing it in this equation will give us rho equal to 11 times this minus 64, and then we know that rho is equal to k over 5, so k will be equal to 5 times rho, as we are interested in the value of k, and this will be equal to 5 times 11 times 17.92 minus 64, and if you find it, you will end up with k equal to 665. So k will be equal to 665, and we know that it is positive because we are on the positive locus. So over here we have k equal to 665, and then as a result, the range of values for which the closed loop system is stable we will have it for k between 0 and 665, and we already had it from minus 32 times 5 over 3 and 0, and therefore for k between these two values the closed loop system will be stable, and for k outside of this range the closed loop system will become unstable, either with one on this side with one unstable closed loop pole or with two unstable closed loop poles from the other side. Alright, so now I think we are done with this problem. We have solved all the points that we were supposed to do. We did this, and this. All the points are done right now. Okay, so then it means that that's all for this video. Thank you for watching, and see you in another video.